0.55 today, right? This will not be part of your first test materials, but in an effort to find a test day where it feels less stressful, we're going to continue past the first test material so we don't waste some empty days. Is everybody good? Okay. So we're going to continue talking about integration here. And the idea here, we're going to see a new integration technique because our antiderivative rules can only get us so far. Suppose we're asked to find the indefinite integral of 2x times the square root of 1 plus x squared dx. This looks like a mess by our antiderivative rules, right? There's no antiderivative rule that even comes close to being able to deal with this because we have the product of two functions and then we have like a composition of a, you know, like the 1 plus x squared is composed inside of the square root. Yuck, right? What the heck am I supposed to do with this? Well, what we're going to do is we're going to use something called, thank you. We're going to create something called the substitution rule. And the substitution rule is going to be our antiderivative trick for dealing with chain rule derivatives. So this substitution rule is going to be the way to go backwards through a chain rule derivative. Everybody's okay with that plan? I don't want my thingamajigger. So let's just notice that if I have an integral of the form f of g of x times g prime of x dx, then my antiderivative, or my integral of that, should just be the antiderivative of f composed with g of x, right? If I have the derivative of g of x times the derivative of g, that should just be the antiderivative of f composed with g. Just the reverse of a chain rule, right? If I look at this, this looks like the chain rule output. So the integral should just be the starting conditions for that chain rule. Everybody's okay with that idea? So in practice, what we do is we're going to introduce a new variable that we'll call u. And we want to let u be that g of x function, the inner function. And we want to make the derivative of u with respect to x equal the derivative of g, or really, we want to make du equal to the derivative of g times dx. So if I take this mess, if u is equal to g of x, and du is equal to the derivative of g times dx, then that just simplifies down to the integral of f of u du. That now looks like something I'll be able to find an antiderivative rule to use. So again, this is just me formalizing that notation. Let's go back and look at that original problem that we had showed you that looked like, I don't have any idea what to do with this, to see if after we introduce this idea, if we can go back and handle that. Okay. So we had the integral of 2x times the square root of 1 plus x squared dx. The first thing I want to do is identify what I want my u to be. What should u be? It's not going to be the square root of 1 plus x squared, just the 1 plus x squared. we always want to pick the u to be our inner function. So like, think about it like a chain rule problem. You want the inner function to be your u, right? And now what we want to do is we want to calculate du dx. So the derivative of 1 plus x squared is 2x. And if I multiply both sides by dx, I get that du should be 2x dx. Is everybody okay with that? So u is the 1 plus x squared, and 2x dx is my du. So this integral now becomes the square root of u du. So far, so good? So we probably want to think about that as u to the 1/2 du. So it's the antiderivative of u to the 1/2.
Over 2.
Okay. Good. Or really 2u to the 3/2 over 3, right? And now my last step is going to be to put the u back in. And really, what should have we had here? A couple of places. Yeah. But that's the gist of it. Look at how easy that integral turned out, right? It looked, to first glance, this was something I have no antiderivative rule to deal with this. What the heck am I supposed to do? It's like, oh, it's just a reverse chain rule, and the way to kind of cope with that is we do this, what's called u substitution. And that allows us to handle things pretty nicely. Let's do some more examples. Yes? Yes. Okay. So let's say we want the integral of x cubed cosine of x to the 4th plus 2 dx. What should our u be in this case? Excellent. X to the 4th plus 2. And our du dx is? Okay. So our du is? Now, if I go and I look, do I have a 4x to the 3rd dx in my problem? I have x to the 3rd dx, but I don't have the 4. So all I'm going to do is I'm just going to divide both sides of my equation by 4. And instead of substituting in for du and trading that out for a 4x cubed dx, which I don't have the 4, I'm going to trade out the x cubed dx for a du over 4. Does everybody see how I did that? Yes.
Like the du always has to equal whatever the other.
Yes. Yes, absolutely. We'd call that the leftovers. Everybody feel okay so far? Now let's pull that 1/4 out to the front. And what's the integral of cosine u du? The antiderivative of cosine. Sine. And then now all we have to do is put in our u back in. And we're done. Which hopefully feels pretty good, right? It's not too bad, right? Just a natural extension to the stuff we've already been doing. It's beautiful and all algebraic, and we don't have to like do any graphing or build any Riemann sums or any like infinite limits or anything weird like that. It's just kind of using our derivative rules. We just have to make a substitution in the first place to get in a place where I can use those anti-differentiation rules. Elena.
What happened to the x?
So the x cubed and dx, I replaced with the du over 4, right? So that du over 4 replaced the x cubed dx. Does that make sense as to where it went? Why? So what we're trying to do is we're trying to undo a chain rule, right? So what we want is the inner function, and then we want the derivative of that inner function. So that's what we're trying to do here. So when we make that substitution, we're going to be left with something we have an anti-differentiation rule for, as opposed to where we started, where we don't know how to do the antiderivative of a product of two functions. What do we do with that? We don't have any rule to handle that. So we did this substitution to get us into a place where we have antiderivative rules now. Okay? So, Katie, I would say if we go back and we look, right, let's just do it to the side or something. So remember the chain rule says that if I want the derivative of f composed g of x, that's the derivative of f of g of x times g prime of x, right? So if we let u equal g of x, and we say du is the derivative of g of x times dx, then the integral of that chain rule can just become f of u du. Oops. So when we integrate that, that would just be f of u plus c. And if we plug this plug the u back in, there we've recovered the original function that we took the derivative of to start with, right? So that's the idea, right, with this u substitution, is I want to take whatever that inner function is from my chain rule. We're going to set that to u. The derivative of the inner function needs to be my du. And once I've made that substitution, I'll be down to a single function. And those are things that we can do the antiderivative of, because we have rules to deal with that. Does that feel any better? Okay, a little bit. It's one of these things, like once you kind of get the hang of it and you see it, will be good. Okay. What if we want to do the integral of the square root of 2x plus 1 dx? Again, notice we don't have an antiderivative rule to handle this, right? Because we have one function composed inside of another. What should we let u be in this case? 2x plus 1. And the derivative then of u with respect to x is 2. So du should be 2 dx. But I don't have a 2 dx, I just have dx. So what am I going to do? Yeah, I'm going to divide by 2. So when I make my substitution now, I'm going to have the square root of u times du over 2. Because my u went in there, and my du over 2 went in there, right? You guys can see the substitution happening now. Okay. Let's pull the 1/2 out front. Rewrite the square root of u as u to the 1/2. And now the antiderivative rule should be pretty straightforward, right? The antiderivative of u to the 1/2 is 2u, or 2u to the 3/2 over 3. I just did it because we've done that one already today. Plus c. I notice that can reduce. So I'm going to have 2x plus 1, plugging in back in for u, to the 3 over 2, all over 3, and then plus c. Just doing okay? All right. Let's take a look at the next one. What should I pick to be my u here? I would not make that as my choice. Let's recognize what's the antiderivative rule that we want to apply in this situation. Oh, well, I guess it's fine. We can do it that way. I would have thought, where's my mouse at? Mousey, where are you? There we go. I would have thought maybe looking here, but that's a 1, not an x. I got turned around. But it still, I think we could make, oh no, because it's squared. No, I think it's, yep, would not have worked. Okay, I was wrong. Good job, Rita. It's okay. Sometimes it just, yeah, it just works out. Let's try it, right? So the derivative is negative 8x. Get the du by itself. Oops. Now, I see the x and I see the dx, but I don't have the negative 8. So we'll do that, right? So I'll make my substitution. So we'll pull our constant out front. And then I'll rewrite 1 over the square root of u as u to the negative 1/2. What's my antiderivative rule going to give me there? Oh, guys, it's taking too long. Good. So those can reduce. So I have negative, we'll have the square root of 1 minus 4x squared all over 4. Oops, plus c. Yeah.
It's like the square root. 1 minus 4x squared.
Because it's the use to the 1/2 power. Back. Right. So remember, like, if we do like the integral of x dx, right, and then the dx is just part of that integral symbol, right? That telling you like stop your integration. Yeah. Does that feel okay? Okay. Is this going okay? All right. Integral of e to the 5x dx. What should our u be? 5x. And then du dx should be 5. So du is 5 dx. Do I have a 5 dx in my equation? No. So what do I need to do to it? Divide by 5. Everybody feel okay? So we'll do our antiderivative. What's the antiderivative of e to the u? And we just plug our u back in. That was an easy one, right? Now let's look at the next one. This is going to be tricky, right? You look at this and it's immediately looks problematic. What appears to be the problem here? What would be the obvious choice for you? 1 plus x squared. When you take the derivative of that, what are you going to end up with?
2x.
And then that means we have like leftover x's somehow, right? Let's see how this plays out. This is the correct u. So just using these two substitutions, let's see where we're at. We'd have this, right? Does everybody agree? And what's the problem here? We still have x's, right? We can't really start integrating until it's all u's. This is going to be my key, is I'm going to have to work with this a little bit more. So if I subtract 1 from both sides, u minus 1 should be x squared, right? And if I square both sides, u minus 1 to the 4th, or squared, should be x to the 4th. That's my additional trick. So that gives me 1/2 the integral of square root u times u minus 1 squared du. Everybody happy with where we're at so far? It's good because we have all u's, right? Everything is in terms of u. So it looks like we're going on the right track. But how do I integrate this? Square root of u times u minus 1 squared. Yeah, very good. So Rita says we got to FOIL this out and then distribute the square root of u through. So let's write it out, because for some of us it's like maybe doing this kind of idea for the first time. Does that all look okay so far? So I FOILed out the u minus 1 squared and then distributed the u to the 1/2 through. And now we're ready to do some anti-differentiating, right? So add 1 to 5/2, I get 7/2. Add 1 to 3/2, I get 5/2. Add 1 to 1/2, I get 3/2. And so if I simplify this down, if I distribute that 1 or that 2 through the bottom, that's going to nix all the denominators, right? So if I plug back in my u, I have, we said it was 1 plus x squared to the 7/2/7 minus 2, 1 plus x squared to the 5/2/5 plus 1 plus x squared to the 3 over 2 over 3 plus c. So the takeaway from this example is, just because at first glance it looks like, ooh, maybe I can't do u substitution on this, sometimes you have to do like a double substitution, right? Where you have to take whatever that initial u is and rearrange it a little bit to make a second substitution. Everybody catch that? Important example. But that was rough, right? That was rather complicated. All right. Let's do the integral of tangent x dx. Remember, for your integration rules, there is no antiderivative rule for tangent itself, right? How are we going to do this? Yeah, let's rewrite tangent as sine over cosine. Great idea. Right? Always got to remember those trig identities. They never go away. All right. So now if we pick this, which one seems like our choice for u and which one should be the rest? Well, here's what I would be thinking. I want that stuff to probably be my du because that's being multiplied together, right? So I probably would want to pick cosine as my u. If I had done the reverse and I had chosen cosine, or if I would have chosen sine for my u, I would have gotten cosine times dx should be my du, but I don't have cosine times dx. I would have had 1 over cosine times dx, and that wouldn't have worked, right? It's one of those, like, if you try it, you would have been, hi, Giselle. You would have been pretty stumped. All right, so we have 1 over u times negative du. So what's the antiderivative of 1 over u? And then absolute value around the natural log. Why do we need an absolute value when we do this? Can't do the natural log of a negative number. We should say non-positive because 0 is a problem also. But that's excellent. And then we just plug in our u, and we are finished. And the u we picked was cosine. Now, is this the best we could do? Like, that's an answer. That's fine. I boxed it. negative out front's the same as like -1 times, right? What do your logarithm rules tell us you can do with a coefficient in front of our logarithm? Make it an exponent inside the logarithm. Oops. And what's the reciprocal of cosine? Secant, or 1 over cosine, which is secant, yep. And that's maybe even a better answer. It's a little bit more simplified. I wouldn't have marked the first one wrong, surely, just so we're all clear. But if it's a multiple choice AP exam question, very likely they're going to give you, natural log of secant x plus c. All right. So the natural next question is, how does this change if I'm doing a definite integral instead of an indefinite integral? Right? Because we're doing this substitution, and there's two different ways you could think about this. So one way is you can do what we've been doing and plug our u back in and leave the bounds of integration the same. That's kind of the natural thing to do. The other option is we can update our bounds of integration and never plug u back in, which if you're doing it by hand can be quite helpful. So let's see what this looks like in comparison to the two methods here on this next example. Sound good? All right, so we've done this problem already, right? The integral of the square root of x, or square root of 2x plus 1. So we said u was going to be 2x plus 1. Du over 2 is going to equal dx. So we do the integral of the square root of u, or 1/2 square root of u du. So that was going to be u to the 3 over 2, 2/3, oops, just 1/3 because the 2's canceled. And then evaluate that from 0 to 4. Oops. And we'd want to plug our x back in here. I should do that. And then we're going to evaluate from 0 to 4. Everybody's okay? Alternatively, I can update my bounds of integration . And that is really a problem I can do in my head at that point, right? Square root of 9 is 3. 3 to the third is 27. Divided by 3 is 9. 1 to the square root of 1 is 1. 1 to the third is 1 over 3. That's like 8 2/3. And kind of the yuckier your u is, kind of the better deal, like updating your bounds of integration are at the start, particularly if it's a no calculator problem. You'll often be quite well rewarded in like knocking down some of the pain in the butt calculation by doing that. So let's try a couple more examples. I think this is basically the last stuff, the last idea here. Maybe there's one more after that, but okay, let's try this one. What should we let u equal? 3 minus 5x. So du dx is negative 5. So du over negative 5 should equal dx. Let's update our bounds. So u of 1 is going to be 3 minus 5 times 1, or negative 2. And then u of 2, 3 minus 5 times 2, which is negative 7. Does everybody feel okay with what I've done so far? Okay. Let's pull the constant out front. I'm going to rewrite 1 over u squared as u to the negative 2. And then I would probably do one other thing here. Do you notice anything weird about our integral here? Yeah, the bigger bound is on the bottom and the smaller bound is on top, right? What's the rule of what happens when we switch the bounds? It makes it negative. So I'm going to drop the negative sign out front to put that maybe back in the proper order. Good memories on that rule. Now let's do our antiderivative. And I would be fine at that point, just probably leaving it. I think this comes out to be 1/14 if you make your common denominators and all that jazz. Remember, is the AP going to care?
No.
No.
Yeah.
Really, at this point, you could have stopped. Unless it's multiple choice, right. If it's a free response question, like make the substitution, put the numbers in, and you don't have to finish it. They needed the values plugged in. They would have needed the fundamental theorem of calculus plugged in.
Oh, right.
In the yellow circle, you could, yes.
Okay,
Yeah, that would have been enough on a free response question, yes. All right. I'm going to skip a couple examples and go down here. So this is the last idea. And this is a minor idea, but it's a helpful shortcut. So this says if f is an even function, and I'm integrating from negative a to positive a, that's going to be the same thing as 2 times the integral from 0 to a. So if we think about just like y equals x squared, and we go from like -2 to 2, the area under our curve is the same on both sides, right? Because an even function is symmetric about the x-axis or the y-axis, right? So that's all it's saying. The second one is the one that's even more useful, though. Look at this one. If f is odd, and I integrate from -a to a, doesn't matter what the function is. As long as it's an odd function, the integral is 0. I've definitely seen in the multiple choice them give you some terrible odd function that would be just time consuming as heck to try to integrate, where they want you to notice that, like, oh, it's an odd function that I'm integrating from like -1 to +1. Oftentimes they're trigs, which is even more, they'll be like -π/2 to +π/2, and you're like, oh, goodness gracious. It's going to be a nightmare if I have to remember my unit circle stuff. No. They want you to observe that it is, odd or even. Okay, so if I look at this one, x to the 6 plus 1 is odd, even, or neither? Even, how can you tell? It's not just the degree of the polynomial. Because if this was x cubed or x to the 6th plus x plus 1, it's neither. If you have a polynomial, the degree for each term must be even for the polynomial to be an even function. What's the degree on 1? It's not 1. It's 0. Because it is 1 times x to the 0. So this is even, because the degree of each term is even. Is everybody okay with that? And that's the shortcut, right? If it's a polynomial, if the sum of terms are each even, then the whole function is going to be even. If the sum of the terms is odd, the whole function is going to be odd. And that could include trigs, right? Like cosine's an even function. I could tack x to the 6 plus 1 plus cosine, and it's still even. All right. So we can do that. But that's not a big deal because this is a super easy antiderivative to take, right? I'm not even going to bother with the 0. I'm just going to write 0 because when I plug 0 into either of those terms, they turn into 0. And that's my end. Whatever. I don't care what that comes out to be. Me particularly. I mean, I could find the common denominators and do all of it. Like, so what? I don't want to. Rita.
So you have to add the degrees, like the sum of all the degrees.
Nope.
So
just each individual degree has to be even. Yep.
What if there's 3 terms and 2 are even?
It's neither. Can't use either of these 2 rules.
So
you'd have to do it by hand.
All even out.
Right. Correct. All right. Let's take a look at this next one. The numerator, tangent. Is this odd or even? What's the graph of tangent look like? It looks like that, right? Just one period of it. Looks like that, right? Is that odd or even? Odd. Because it's like, has that like double symmetry, right? If you reflect it across the x-axis, then they're reflected across the y-axis, they lay on top of each other. Or if it just like catty-cornered, that's the way I think about it. So that's odd. What's the denominator? Even, because the degree of each term is 0, 2, and 4. So that's an even function. If I take an odd and divide it by an even, what kind of function am I going to get? I'm going to get an odd, right? So like, notice here, if f of x is g of x over h of x, and g of x is odd, h of x is even. So if I do f of negative x, I'm going to get g of negative x over h of negative x. Since g of x is odd, the negative sign comes out front. Since h of x is even, the negative sign just gets absorbed. So I have negative g of x over h of x, which is negative f of x, which tells me f of x is the odd, right? What if I had odd over odd? What's that going to be? Even. Even over even? Even. Everybody's cool? So, or does it work the same way for multiplication? Yes. So since this is odd altogether, what's the integral got to be? 0, because we're going from -1 to +1. Do I have to do any more work other than showing that the function is odd? Nope. Which is beautiful, right? Okay. I need to pick some problems I was not prepared to assign homework today, so I didn't pick any problems here. That's okay. Okay, so I just have like a bunch of these things that are all just like do the integral, right? How is this going so far? Integration is going okay? I think in a lot of ways it is. Like now, in practical terms, like for what we're doing, I think the integration is the easier of the two operations. In general, integration is much harder because not every function is integrable. And sometimes the integration for that function is like absurdly difficult in a way that derivative, like differentiation of a continuous function is never that difficult. Like it can be time consuming and tedious, but like I can make as complicated of a function as I want. It's still just like chain quotient, product rules, and our derivative rules, and it's doable. Like we have all the tools you need. I can make it like just terribly complicated, but it's like I just have to be careful and it's doable. I ask you to integrate the same thing. Yes. Sure. Yeah. Yeah, 1 second, real quick. Why don't you do 31 also? Okay, and then we have to pick some problems here still. Yes, what is it, Jacob?
So on my Notre Dame, I noticed that I'm like missing homework quizzes from like when people were rating stuff. Are those something I have to do, or did we not ever do this?
So we did the 2 on my AP, and then all the other ones we haven't done.
Okay.
This is the first homework quiz we've done from chapter 5, was the one today.
Okay.
So I think I was updating things this morning, trying to get that all squared away.
Mark Farrell made this all sound a lot harder.
It can be very hard, but like It doesn't have to be.
Right.
It doesn't have to be, and it won't be for a while. But it can get harder. Some of the application stuff is quite hard, but I still think the hardest application stuff in this for integration is no harder than the hardest application stuff for derivatives. I think oftentimes it's actually easier because it's a little bit more like, after a while, like you realize that all these problems are kind of the same,
Yeah.
and they take much less creativity.
Do we do polar coordinates later?
We do not do polar in the AB course. That's a BC problem. And we do a little bit of BC stuff, but not not a ton. I need one more.
Farron's already done teaching himself PC. Probably just something to offer, but he's doing it on his own.
Okay.
So we did 115.
Okay. So that looks good. There's some numbers. I picked some stuff. Oops. Did you guys get a chance to look at any of the MCQ or FRQ stuff that I put in there yet? Okay. Try to look at a little bit of that between now and next class so we can talk. We'll probably have a similar amount, like 10 or 15 minutes of extra. That would be nice to talk about, because I think, yeah, that's not a big, 6-1 is not big. So we can do talk a little bit about that stuff next time also. That makes I think makes pretty good sense. Yes, Rita. Oh my gosh, I should have. Yeah, let's do it. Yeah, hold on, guys. Thank you. So we're going to do some homework questions from previous sections. So Rita's got one from 5.4. 61? Yeah. All right. So it says the acceleration and initial velocity for a particle moving along a line are given. In part A, it asks to find the velocity at time t and then the distance traveled in that same given interval. So I know that v of t is going to be the integral of a of t dt. So that's going to be t squared over 2 plus 4t plus c. And since v of 0 is equal to 5, I can say 0 squared over 2 plus 4 times 0 plus c has to equal 5, or c is 5. So v of t is t squared over 2 plus 4t plus 5. That's part A. And then for part B, it wants the distance traveled. So that's going to be the integral from 0 to 10 of the absolute value of v of t dt. So I'm going to take my take my velocity equation and set it equal to 0 and solve that. Oops. Okay, so if I think about my graph then, here at like -4 minus root 6, and then we have -4 plus root 6. Oh no, those are both going to be fine. They're both going to be over here. So it's going to look like that. Is that okay? What that tells me then is this is just always, it's positive from 0 to 10. So I should be good. Just do it regular, because there's no part where the velocity is negative.
If it is negative, then what, you have to like break it into the
Yeah.
parts? Like you have to do like integrate from 0 to 8.
Yeah, or possibly like 3 parts.
Right.
You know, just, and the part that's negative,
Absolutely.
I have to absolute value the answer.
Right.
But
The graph here, like why, like, you have value.
because we're integrating from 0 to 10, so the graph is positive the whole time from 0 to 10.
So like,
Right.
It has like negative stuff, then
So what I did is I solved my equation equal to 0, right?
It's only negative outside the interval.
oh, so like you only have a problem if it's like negative, then you have to do like that. So it's positive.
Yeah. And because the leading coefficient is positive, I know between the zeros, you know, we're opening up, so it's only negative between the zeros, and both the zeros were negatives, so it was not as bad as it looked. I think that
Yeah.
looks right.
It's about that.
Yeah, and that is definitely something that I would, Mr. Kulik would put on a test for sure, asking you to integrate an absolute value function.
Wait, nobody else's questions? We have 59 as well.
Sure, I just want to look at my answer book real quick and make sure that we didn't goof that up at all. This is, I was like, that's not the right problem. I was in the wrong section. Yeah, good, okay. And you said 59?
Yeah,
B, that's similar problem, right?
yeah, but like, we do like the absolute value.
Yeah.
Okay.
Yeah, that's okay. Okay. So here it gives you the velocity function, which is lovely. Oh my goodness, come on. So, and you wanted just part B, you said?
Yeah.
Okay.
Part A was fine.
So we're integrating from 0 to 3, the absolute value of v of t dt. And if I just think about the graph here, so we're doing something like that, right? So I just care about where it's equal to 0. So that's 5/3, right? Oops, 5/3 to 3. Does that feel okay? So it's going to be 3t squared over 2 minus 5t from 0 to 5/3. And then we got to absolute value that bad boy. And then this one is just same thing. But here from 5/3 to 3. So that's, and then you're just, yeah, everything is substituted in. You just have to grind out the numbers at that point.
It's like the reason that's why I don't want to see like the absolute value. Like
The other option, Rita, again, you could think about it this way also. You could do that and stick a negative sign in front. And that's okay. Because I know that this area is going to be negative. So by doing the negative of the negative area, I've done the absolute value to it. So remember our... Right, that's the definition of an absolute value. So if I know the absolute value is negative, I just make it negative. And that, so that's what I'm doing here. So like if I do absolute value of -5, that's just like, I do that, right? So I know this is going to be a negative area. So if I know it's going to be a negative area to the absolute value of it, I just take the negative of it.
Oh, if that's in the range.
Yeah.
Okay.
You're welcome. Does that feel good? Bye.